Welcome to Planet Geo, the podcast where we talk about our amazing planet, how it works, and why it matters to you.
Good old mom coming through again.
It was a good day when we get an email from Joyce, Chris. Have you read the email from Joyce?
No, she said one's on the way. She
did. Okay, so
texted me and said, "Hey, Chris, I've got a question for Jesse or something like that." Right? Is that what it is?
I don't know if it's not really a question. It's a comment. It's Joyce's word of the day, which is a theme I would love to continue on with. Because we had one word of the day, which was feldspar. Was it feldspar or something like that, or anorthosite? She had some word that she really enjoyed. That was a mineral from years ago. You don't remember this?
I don't remember, but she does make a lot of comments about words that we use, and she's enthralled by this new vocabulary.
Good. We're introducing her to a whole new world of geology vocabulary. This one's not. So Joyce's word of the day is bedraggled.
Bedraggled. How does that fit into? Was it like a recent episode that we had?
Yeah. So she says bedraggled is an adjective, and it's of a person or person's appearance. Messy, dirty, and often wet. Jesse's description of Chris being under the weather. I think when you were sick a while back, I called you. I said we had bedraggled Chris.
Wait a minute. You actually used the word?
I used I said we have a bedraggled Chris with us, or something along those lines. And messy, dirty, and often wet. That just fits you. It fit you perfectly.
Was Mom Bullheis offended that you referred to her youngest as bedraggled?
No. She ends with, "I just love that." So okay, I think it's a compliment.
Right.
Don't you?
I have
Is
to
that
have
a
words
compliment
with my mom?
Joyce?
Apparently, I don't know. I'll find out. I'm going to see her later today, I think. So
okay, ask her if it's a compliment. I like this. Joyce's word of the day. And tell her we need more words of the day. Send in her word of the day emails more frequently because they're always a delight.
Okay, well, I'm really trying to think of that word that we used that she was so impressed by.
My memory is terrible, but
it was not a geologic word. It was just
No, I think it was a geologic word. I think it was. I think we were talking about anorthite, or I'm not sure, plagioclase or something. Some feldspar composition. I could be way off.
I don't know. I can't keep up with my mom's wonderings about what we talk about. They get shoved to the way back of my head sometimes.
Yeah. So. Of course. Well, has had any good comments when you go over there on Fridays recently about the pod?
I just have to wake her up.
Oh, okay. Yeah.
or I'll just start talking about what we're talking about, and I'll wake her up that way and kind of bring her back into the world.
Bring her back into the fold. So, yeah, that's good. That's good. Well, hey, we got one regular listener. It's Joyce. Love it.
Yes.
So good. Well, Chris, today we're talking about a big fancy word that's actually really basic. I'm curious your thoughts on this. Is the word hypsometry needed? Do you think?
No. Short answer is no.
I agree
hypsometry or hypsometric curve. I did not know. I had to look this up, actually. The root, what does hypso mean? And I didn't know.
I didn't know the root either. Yeah.
So think about that, our listeners, please, just for a quick second. What does hypso mean?
Yeah, if you could take a guess, because this is a really fundamental, This is something you learn in every intro level class. Not this curve, but you learn the underlying principle. And then the fancy scientists over here, we have to add some complex word to it and add metric. So we're measuring something, but a hypso is aloft or high or height or something to that effect. So it's height, it's aloft, it's high. So it's a completely unnecessary term, right? Chris, you
guys doctored this up real good.
We did. We made it. We have to make it inscrutable to the average person who doesn't know all these words. I mean, it's ridiculous. So hypsometry, but this is a really, really, I love this concept. Basically, it's the crustal distributions. Think about Earth. Let's take all the oceans away. And if we had a map, we don't actually need a map. All we need is a elevation distribution. So like how much percent of Earth's surface is between 0 and 1 kilometer above sea level? How much of Earth's surface is between 0 and 1 kilometers beneath Earth's sea level, et cetera, for all the elevations? How much of the Earth's surface is more than 6 kilometers above sea level or more than 5 kilometers? Like, it's a distribution.
That's right. And it's expressed as a percentage, really, of like, all right, here's the Earth, here's the surface of the Earth. What percent of it is just above sea level, just below sea level, really, really far below sea level, and then
Exactly.
really high above sea level. So as you said earlier, you would come across this in any intro level geology course or geoscience course. We think of it as a passive continental margin. This would be the trailing edge of a continent, basically, where you have this continental shelf, just really flat area, just above sea level and just a little bit below sea level. And then you get this continental slope where it dives down toward the deep ocean basin, where you have this transition, the continental rise, and then finally the abyssal plain. So every geology course is going to show this very idealized profile of the Earth. And then this hypsometric curve just adds in the high elevations and the really low elevations like the deep sea trenches. So it's a little bit different take on a basic concept.
You nailed it here. The curve itself, so this is a curve that is database, but it looks exactly like a profile of a continent transitioning to an ocean. Let's build this a minute because, and let me back out of this. Why are we talking about this? To me, this is an entire lecture that I give in my intro level class. And Chris, I'd be curious to know how you aggregate these concepts or how you talk about these concepts. But I spend an entire lecture on this because it's really cool to me that you can look at just the distribution of elevations on Earth, and we can infer, as geologists, and people have done this back in the day, you can infer a ton about our planet just from that. Some really important first principles. So the kind of thought exercise here is, what happens if we fly our spaceship into another solar system and we look at planets and all we have is like LiDAR, or all we can actually measure is the surface, the topography of the planet? What can we tell about that planet from just topography? That's kind of the thought exercise. We're turning that on Earth. What can we tell about Earth from just the topography of Earth? And there's actually some really amazing stuff that we can tell, I think. So that's why I spend an entire lecture on this. Chris, how do you get these concepts across? I'm guessing you don't talk about the hypsometric curve because it's like useless for high school students to know that word.
You know, I talk a lot about the profile of the Earth and like the continental margins and then leading into the deep ocean. It's just classic. It's an important process. It's an important thing to learn. So hold on a second. You actually do a whole lecture. Do you use the term hypsometry or hypsometric?
I do. And
how long have you been doing this?
This is my third year doing it, I think.
Okay.
It was one of these things. I was reading some papers and I was working on this. I started working on the idea of when continents emerged above sea level, which this hypsometry is kind of, really deep involved in that. So I started like reading papers about this curve, and it's a really basic concept, but it's used a lot. And so then I was like, oh, I could probably use this as a way to explain a bunch of features of Earth, and it actually was used in early plate tectonic theory to derive plate tectonics. So
okay,
that's I don't know. I don't know if it lands totally well or not, but I think
because I'm actually going to use this now because I'm looking at the hypsometric curve for Earth right now, and basically you already described it, but it shows the elevation, whether it's above sea level, at sea level, or below sea level. It shows the elevation on the y-axis, and it shows the percentage of Earth that is represented by that on the x-axis. And so you get this kind of longitudinal profile.
Let's build this a minute because I think it's really important just to visualize so the listener can visualize. And this is going to be a little bit hard to do, but that's exactly the chart. You have elevation on the y-axis, and we're going to go percent of Earth's surface on the x-axis, and we're going to go from 0 to 100%. We're going to compile this. So it's basically it's a total curve. We'll add up to 100% by the end. So what we do is we say, okay, Chris, how much of Earth's surface is above, let's say, 4 kilometers above sea level? Let's start high and go low. So how much of Earth's surface is between 4 and 6 or 7 kilometers above sea level? And the answer is like, what, a couple percent?
Yeah, it's so I would say maybe looking at the curve, I would say maybe 5% of the Earth is above 2 kilometers.
So really high mountains, there's a very few percent. So we're going to go from like an intersection with the y-axis is at like 7 kilometers. It's going to steeply go down to start. So by the time we're on the x-axis, about 5%, we're down to like 2 or 4 on the y-axis. We're dropping down into the right. Then, Chris, we hit continental interiors, which are kind of what, let's say 1 kilometer to sea level. What percentage of Earth's surface is that kind of like 1 to 2 kilometers to sea level area?
So I would say maybe from 15% to sea level, you said?
Yeah, to sea level. Or let's say take it all the way past sea level. Take it all the way
to
past
where
sea
it
level.
dives down.
Like,
so
yeah,
the
continental
from 15
shelf.
to 40 plus percent.
Okay,
Yes.
yeah. So that's like 25% of Earth's surface is kind of between 1 kilometer above sea level to 1 kilometer below sea level, roughly somewhere in there. So our curve it steeply goes down when it hits like 10-15%. It flattens out because a large percentage of Earth's surface is right at that narrow interval between 1 and -1 kilometers relative to sea level. So the curve flattens out. Then we hit the edge of the continental shelf and we get to this sort of transition towards the abyssal plain, which is how much of Earth's surface is between -1 kilometer and -4 kilometers. There's not much that's in that transition area.
No,
So our
less than
curve,
10%. Yeah.
less than 10%. Yeah, like 5-7%. And so our curve now is going to steeply drop again. And once it hits about -4 kilometers below sea level, we hit the abyssal plain, which, I mean, you could just look at a map of Earth. There's a lot of the ocean basin. That's that area, right? I mean, I don't know. I'm looking at this chart. It's like 50% probably of Earth's surface.
50 plus percent is
50 plus,
deep,
right?
deep ocean. Yes.
So that curve again kind of flatlines for a long time and goes until we're far to the right on our x-axis. We flatline far to the right on our x-axis. Now the question is, how much is really deep trenches? The deep trenches, again, a couple percent, 5,
Yeah,
7.
very small percent. Yeah, probably less than 5%. Yep. When we're talking about things like the Tonga Trench or the Mariana Trench, these deep ocean trenches, yes.
How much area is that? It's not much on Earth, right? We can look at a map and determine that. So our curve, again, plunges down until it hits 100% on the x-axis and like -11, -12 kilometers on the y-axis. So our curve, let me just summarize that. It's like starts at the top left at the y-axis, dives down quickly, then flat lines in the continental interiors, then dives down again pretty quickly till we hit the ocean floor depth. And the ocean floor depth flat lines for about 50% of the x-axis until we get close to 100. And then it dives down again really deep where the trenches are.
So, Jesse, my plan now, as you've been rambling on here forever, I formulated a plan.
Okay, good.
So I
Chris, let me rephrase
this.
that. Well, I'm trying to paint a beautiful visual for the listener.
My mind is elsewhere at that point.
Yeah,
Sorry.
that's fine.
And so was everybody else's, I think. But anyway, sorry, Dr. Rybank. I mean,
it's quite all right. And guess what? So were my students last week, Tuesday.
Here's what I think I'm going to do, Jesse, is I'm going to use the hypsometric curve. I'm going to give it to them. They're going to get into their lab groups, and I'm going to have them think about this without me talking about it. I'm going to have
That's a great idea, Chris. Do a lab on this. That's a great idea.
Exactly. Like what you just did of breaking down the percentages of the different segments of Earth. We have the mountains, we have the plains, we have the broad continental shelf.
Okay, this is a really good lab exercise that I want to know either how it goes or if I keep teaching the intro level class that I currently teach, revising our labs would be good and adding a lab in like this where, so are you thinking you look at a map and actually derive this curve, like make up this curve by looking at the topographic map of Earth? And then
no, I wasn't thinking that. I was thinking about looking at the hypsometric curve, something that I've really never used before, and saying, all right, well, let's first get the breakdowns. What do we have here? They're going to be able to derive, well, we have mountains. We have this really broad plain that is just above sea level or just a little tiny bit below sea level.
Oh, I like that.
Then we have this deep dive to the deep ocean basin, right? And so they're going to come up with, we've got mountains, we've got this broad shelf, we have the rise, we have the abyssal plain, and then we have these deep trenches, and then assign percentages to that, right? So that's a start, okay? Just interpret the graph. Then what I want to do is, all right, well, what kind of inferences can we make then from this data? This is real data. What can we make inferences about the small percentages? And let's have our listeners start thinking about that a second. If we have a small percentage,
because this is where we're going.
Earth,
this is the point, and this is where we're both sitting up straight in our chair. I mean, this is where we're going with this entire episode. So yeah, I like this idea. This is great. So do you envision taking how much, I'll be curious about this, and we can use this for the podcast too. How much help do you think students are going to need to get to the inferences that we're going to talk about here, that you and I have talked about and we're going to cover? Like, do you think your students are going to need a lot of help?
No, I don't.
No? Okay.
No, they're going to need some help.
Let me ask a second question. When do you envision over the course of the course doing this? In the beginning, at the end? Like, how much information do they need? I guess those are two related questions.
Okay. It won't be right at the beginning because they're going to need some background information. They're going to need to know the types of crust that we have on Earth. We have two types of crust. We have oceanic crust. We have continental crust. So I want to already have talked about that. And no, I don't think I will have already discussed the longitudinal profile of a passive continental margin, of the continental shelf, slope, rise, and abyssal plain. I won't do that yet. So kind of in between those two things is I want to introduce the hypsometric curve.
Gotcha. Okay.
So I think what they're going to need, they're pretty quick. My students are pretty quick. And so they're not going to need a lot of help. They're going to be able
they're well trained.
They're going to get to, they're going to be able to deduce, we got mountains, we got this broad plain and so on. They're going to get the 5 basic areas that I'm looking at on this hypsometric curve and assign percentages to it. They'll be fine with that. They don't need any help.
Yeah.
Then what kind of inferences? They'll need a little nudge. And so I'm going to maybe give them keywords about maybe like, all right, think about stability. What is stable and what's not stable based upon the percentages?
I like this a lot, Chris. I want to know how this goes for sure. And if you're listening to this podcast and you're a teacher and you want to know how this goes too, send us an email and you want to use something like this because I love this idea and I want to use it. I couldn't use it this semester, but next year we could revise the labs and there's aspects. We have labs that are kind of old and I would love to revise a few of them and do something like this would be kind of very thought-provoking and cool. So yeah. Okay.
All right. So it's going to be a minute because I don't get my geology students until November.
No, that's perfect.
So right now I'm teaching astronomy. So I'll get my geology students in November. Then it'll take us a little bit to get that far. And then I'm going to definitely do this.
Sort of in the new year or something like that. I like that idea a lot, a lab on this. Okay, so let's walk the listener through this lab to the end goal is to get to these really, really amazingly basic but really important inferences. So the first thing that we can do, Chris, for me, this is the one that stands out to me. Again, we're pretending we're like from outside the solar system coming in and all we can do is map the Earth in topography. So we've got a LiDAR thing that goes around and that's about it. What stands out is the flat parts of the curve, and the flat parts here mean that there's a lot of crust that's very similar elevation to a lot of other crusts. So the continental interior is that +1 to -1 kilometer elevation. There's like, what we say, 25-30% of Earth is that. That's all one thing. And then the other flat part is the abyssal plain, -4 to -6 kilometers below sea level. That's like 50% of Earth's surface. So those two things stand out. And what basic inference can we say with that?
Well, if I'm going to nudge him and I'm going to say, all right, let's think about stability then. Well, because there's such a big percentage of those two types of crust. When you look at the curve or when you look at that longitudinal profile of a passive margin, the part that is just above, at, and just below sea level, it looks thicker. Right. And they'll know this. My freshmen know this, that the continental crust is thicker. It's more buoyant, it's less dense, and this curve clearly shows that. And then the other kind of crust is the oceanic crust, and that's the deep part of the ocean. That's the abyssal plain. It's much thinner, it's denser, and it is the antithesis of buoyant. It's with plate tectonics, it's what's involved in subduction and so on. So those two things.
Exactly. We have two plateaus, they're different elevations. And what we can infer from that is we have two different types of crust on Earth, which is very basic, very first principles thing. We have two types of crust. One of them's thicker or more buoyant. It's actually both. One of them's thinner or more dense. It's actually both. We have oceanic crust and continental crust. And, we wouldn't need to name them that. We wouldn't need to know that one of them's below the ocean floor and one of them's at near the surface to understand that there's two types of crust. One's thicker, more buoyant. One's thinner, more dense. Like, that's a really fundamental thing about Earth that we have on Earth that is pretty unique to Earth that we can look at and figure out from the hypsometric curve.
That begs the question then, since there's so much of it, does that mean, Earth has this bimodal crust that you just described? Are both types of crust then stable?
Yeah.
Is that what inference can be made?
I love your intro with the word stability or your sort of...
the nudge.
The nudge with stability, because it's such a great one. It brings up this question. What do we think? I mean, let's think through this. Do we think that it means that they're stable? At first, I would say yes, because there's a lot of it. So I think the two options are either you're creating a ton of it very quickly, or it's stable. it's created and it doesn't decay away, and it doesn't actually change elevation much. It's kind of bobbing up and down. It's very stable. And so let's work through that. Like continental crust, we're producing a decent amount at volcanic arcs and at subduction zones, continental subduction zone systems. But there's arguments that we're kind of destroying continental crust too. So that one to me is more of a stability thing. So yes, I would say that checks the box. There's a bunch of it, so it means it's stable over long time periods. We know that from Earth. What about oceanic crust?
Well, it's different because in oceanic crust, is it being eroded? Does that process happen in a way that happens above sea level? And the answer is really no.
No, not really.
It's not really, not much anyway, not significantly, because it's underwater.
But is it stable?
It is. Is it stable? And if you look at what can happen to oceanic crust, or what is inevitable with oceanic crust, is that it's going to, because of plate tectonics, it's going to be involved in subduction at some point during its lifespan. This is why, one of the questions that Dr. Maddox loves to ask my students on the exam is, how old is oceanic crust? And geologically, it's hard to find oceanic crust that's older than 200 million years.
Oh, yeah.
And geologically, that's really young. And so why? Well, that's because it gets recycled in subduction zones of it eventually. And so it's not stable.
It's not stable. Yeah. Okay. I totally agree. It's not stable. So I don't know that we could really argue for stability based on a large amount of these two types of crust. Now, let's come back to that, because maybe we can, once we kind of put the other puzzle pieces in place that we can figure out using this hypsometric curve, we might be able to get there. At least we can have a hypothesis about it. So let's move on to the next one. And Chris, let's move away from the two peaks in distribution, or the two large areas of Earth that are a certain distribution. Let's focus on mountains first, because I think that flows nicely. High mountains, a small amount of very high mountains. Okay, we can tell a lot from this, but I don't think this is necessarily intuitive. The first one is certainly intuitive. Like when I ask my class, I say, okay, what do high mountains tell us? And usually it might not be the first answer, but one of the first three answers is there's stuff being pushed up. They often kind of get too complicated with it first, and then I need to back them up and say, no, basic stuff. They're like, oh, well, stuff's being pushed up. Like there's stuff going up, which you always say there's two forces on Earth, stuff that pushes stuff up and stuff that pushes stuff down. And we're going to talk about both right now. But
that's right. I'm just saying that because we have such a small percentage of it, means that stuff is getting shoved up. But it also means that the second force is also very much at play. The belt grinder of weathering and erosion is an active process. So if this process is going on and has been for billions of years, then if it was stable, once it's created, it's there. But this curve says that they're not. So they get knocked down.
And so I think, Chris, I always have this discussion in my class before I talk about plate tectonics, because I want them to come at this without having plate tectonics in their mind. Because I don't think that, in my opinion, the fact that we have high mountains and we know that stuff's being pushed up does not mean plate tectonics yet. Because there are other forces that people have talked about that could potentially create high mountains. There's buoyancy stuff. There's this old expanding Earth kind of theories, which have been disproven now. But on a different planet, maybe there are forces that could push stuff up to these extreme elevations that are not plate tectonics. On Earth, we know it's plate tectonics. But that last point you made, the thing about erosion, that's one that my students rarely get to, because, again, I haven't talked about erosion yet. I haven't talked about any of these forces. I give it near the beginning of the semester, like week 2 or 3. But it's an important question. It's an important thing. We know there's stuff being pushed up there. So why isn't there a lot of it? Well, it means the process only just started recently on Earth, or it means erosion. It means that something is knocking it down. That to me is a really cool conclusion you can make just by looking at this curve. I don't know. What are your thoughts?
Yeah, I think so. What we're doing is we're looking at something that is a very, very basic idea in geoscience. The force that lifts things up, the force that tears things down. But we're looking at it from a data standpoint. I've never thought about it in this regard before, actually. Before you brought this to my attention, this hypsometry. It's not a word that I've ever heard before. And I love it, though, actually, because this is something that maybe, like you said earlier, that we can look at Mars maybe with LiDAR or just topographic profile and maybe make some inferences about what's happening on this planet or what has happened on this planet before.
I mean, it's all hypothesis. If this is the only data we have, we generate hypotheses about the Earth. But a very, very solid one is that there's something knocking these mountains down. There's something pushing them up, and there's not many of them, so there's something pushing the mountains down. That's very fundamental, that there's erosion, there's some form of erosion, there's something knocking these things down. And I don't know, that to me is just such a cool leap. There's such a cool little bit of intuition. And this is the beauty of geology to me, is it's fundamentally this like very artistic storytelling science where we look at data and interpret it over long time scales. But it's like we've talked about many times, the basic things about geology, like cross-cutting relations. It's not that obvious unless you've heard it. But once you've heard it, it's really cool and actually kind of obvious and incredibly powerful. This to me is kind of in that category of stuff. These
100%
little bits of intuition. So
this is something that is in education, just in general, the more we can expose younger minds to this idea of looking at real data and then making inferences from it. It's a difficult thing for them to do, but it's definitely something that is emphasized on all of the standardized tests.
Oh, is that right? Okay. This kind
absolutely.
of like data analysis.
Data and graph analysis is absolutely. Yeah.
Oh, I didn't know that actually. I probably should have known that. But on the standardized testing, this is like a big deal for.
It's huge. Yeah, this is so. The more we can come across like really good examples of this, and the hypsometric curve is perfect for that kind of thought experiment. Absolutely,
this would be cool. Yeah, this is cool. If this would be fun to kind of build a lab I mean, you can go, like we've talked about before, into more detail than I do in the college class, and so we might have to make a shorter version for my class, or shorten the one you make in some way, shape, or form. But okay, so can we move on to the trenches?
Yeah, the last one, the last tiny little sliver, the last aspect of the hypsometric curve is these really, really deep sea trenches.
We're going to jump all the way to the right in the hypsometric curve. Between 95% and 100%. So 5% of Earth's area is like really deep trenches. And you said it before, we're talking about the Tonga Trench. We're talking about these trenches that are in the ocean floor that are really, really deep. And Chris, this was used. There's a really cool, we'll talk about this in an upcoming episode, but there's a really cool story to this where people who were doing back in the early days of plate tectonics, like pre-plate tectonics ideas, people were doing a lot of gravity measurements, and they'd take ships and they'd have a gravitometer in the ship, and they'd drive around, they'd measure the gravity field. And, you could see mountain ranges. You probably talk about this in class. You can see mountain ranges. You can see the gravity of mountain ranges. You could see the lack of gravity. They'd drive over trenches. They could see the lack of gravity in the trench. They actually started to piece together plate tectonics because of this, or proposed plate tectonics. And this is a bit of a leap. This is certainly in the hypothesis that needs to be tested category. But okay, if we back up, number 2, high mountains told us that, first of all, stuff was being pushed up and they were being knocked down, and that's likely erosion. So that material, that mass, has to go somewhere. And it's not too hard to understand that it probably goes into the ocean. So then where's that connection between there's erosion happening, but there's a trench? How do we get to plate tectonics from there? That's like a tricky equation. Erosion plus deep trench equals plate tectonics is complicated. How will you nudge your students in this direction?
Well, again, thinking about stability, you'd think, well, maybe because there's such a small percentage of deep sea trenches, are they getting filled by some mechanism? Like, is the erosion from the high stuff on the continental side, is that getting shoved out into the deep oceans and into the deep sea trenches and filling them, thereby removing them?
Okay, there we go. It is, right? Like, we know erosion's going out. It would fill up the trenches. That's a pretty sound interpretation, right? In your mind, do you think
Yes, yeah, because these deep sea trenches are not that far off the shoreline. They're nearer the source of the sediment. It will make its way that far for sure.
So the sediment would fill these up if they were stagnant. So therefore, the fact that the trench exists means what?
That you have two forces going on there as well.
Exactly. Oh, it's so good. You're actively creating the trench too. It's an active process of creating the trench. So because it's so cool. I find this so cool. The fact that the trench exists means, because there's erosion, that we're dumping stuff into the ocean basin. The fact that the trench exists and that it's so freaking deep, 6 kilometers of trench below the abyssal plain, the fact that it exists means that it has to be actively being produced. It's like mountains. The fact that they exist means they have to be actively being pushed up because otherwise they'd be destroyed. The earth wants to be flat everywhere. Just like the processes want to make it flat. This is where the plate tectonics theory, one of the ways that it originated is like, oh wait, there has to be an active process creating a trench. What's a good one? A good active process creating a trench is this oceanic plate diving down into the mantle. That's a pretty good way to keep a trench active over long time periods. So that's certainly a hypothesis if this is the only data we have, but it's a sound one. When we get more data, like it's the simplest explanation for keeping a trench active for a long time. So I love that one because you were kind of building this. We're saying we have two types of crust on Earth. We have mountains that are going up. We also can tell that they're being knocked down because there's not many mountains. So because there's stuff being knocked down, that stuff's going into the oceans. We know it's going into the oceans. So therefore, because we have trenches, they would be filled up if the trench wasn't being actively created. So the trench is being actively created. So we can look at this curve and say, we live on an active planet. It's a pretty good bet that there's erosion and plate tectonics going on, all from the hypsometric curve.
And, this is an interesting thing because I think all of our listeners know that we live on an active planet. They knew that before this episode, but this is just looking at it from a different standpoint than I think many and most people have ever thought about it.
And I would bet, I wanted to kind of end with this, but you kind of answered it already because I know that some of the textbooks have this hypsometric curve, in it and talk about it, but it doesn't feel to me that it's not fundamental. Whereas I've kind of structured my lectures a little bit around it being kind of a fundamental process. And I keep alluding back to the hypsometric curve throughout the rest of the course a little bit, just because it's kind of this fundamental thing, especially when I get to plate tectonics. Do you think, okay, you've answered it because you want to make a lab. So I was going to ask, do you think this is a useful teaching tool? But you've kind of already answered that. But that's interesting. It comes from this data-driven standpoint that students, there's an emphasis on getting students to read and understand and infer stuff from data. I hadn't thought about that before. So kind of with that, I want to ask you a question about back to the stability thing. I could see a way that we end here with there's deep trenches, therefore there's plate tectonics. And what we mean is that oceanic crust is likely diving down into the mantle. So the oceanic crust is diving down into the mantle. Can we bring that back to the stability question? Do you think students would be able to make that connection to bring it back to stability where we talked about stability in the beginning?
So what you're asking is, do you think that they will be able to deduce that the deep sea trenches are not stable?
Or that oceanic crust is not stable, whereas continental crust is. The high mountains get knocked down to continental crust level. The ocean floor gets subducted down trenches. I think we can make a hypothesis link. If you really think about this for a long time, I think you might get there. My question is could students get there? Back to the stability thing and say oceanic crust is not stable, but continental crust is stable.
I don't think right at the outset, but what I envision happening is they're going to then they're going to identify the different parts of Earth based on the hypsometric curve. Then they're going to assign percentages to it. Then they're going to start thinking about what's stable and what's not stable. And they're probably going to say that oceanic crust looks like it's stable. I would expect them to get to that. But then we're going to have a class discussion about that. And so just by asking more questions, kind of like what you and I did walking down from the Tetons 20 years ago.
Yeah.
Is they're going to be able to deduce that no, it's not without me answering it. I'm just going to ask them other questions because they do have a fundamental background in geoscience already because they took my class as freshmen, just earth science.
Yeah, totally. So okay.
They'll be able to get there.
Yeah. That's impressive. That's very cool. I'm so interested to know how this goes. And, we keep talking about this, but
when I think about what I just said to you, Jesse, I think I am so proud of the school that I'm a part of, that I work for, in that we provide a really good background in geoscience. And then with electives, thrown into that, like my geology course and then astronomy, there's a lot of planetary geology that goes into a class like that. Also, it's so unusual, I think, for a public school to have that deep of options.
And it speaks to two things. It's 90% you and it's 10% your administrators, allowing this freedom and flexibility to navigate. And, I went through Huntsville Public Schools and the science department was great then. And it's been great for a long time. I mean, your dad was a great biology teacher there. My dad was a great biology teacher there. The science department has been very, very good in many different fields. And geology is, one of the big dogs that barks there, I think now.
Is.
And you produce,
is a big dog. We have,
but to brag for you, you produce, or Hudsonville produces, I forget what the long-term average is, like 7 or 8 geology majors who end up going on into geoscience. And usually that is a college geoscience degree in some way, shape, or form, and be either teachers or researchers or professionals in the industry, various industries. That's a high number especially for the state of Michigan. That's a very high number. And
I would not
cool.
say, I want to push back on one thing though. It's not 90% me, because I'm only one of 4 people that teach freshmen, all the freshmen that come through our school.
Oh yeah. Okay.
They actually do the most of it, because I teach these other electives for the upperclassmen. I teach geology and astronomy, and so I'm not.
No, that's totally fair. And the summer science thing, you've done that for a long time, but you're half of that team always. And I was more speaking of the upper level stuff. Like you got to create astronomy. You created the geology thing,
yes,
and somebody's going to inherit that, but and hopefully keep running with it. But someone's got to start it. So
right.
I was referring to the upper level stuff a bit, but
yeah, okay, all right. I just want to I don't want to slight anybody. I work with amazing people, and we do I'm just proud of it, because when I think about what my geology students are going to be able to do with this hypsometric curve, I think they're going to do a lot with it, because they already have a really good background in geoscience. So I will be able to hit this early on without having talked about a lot of these concepts in my geology class.
Well, I think that, somebody sitting there listening Joyce is probably like, what the heck are we talking about here? Why are we talking about this? And to bring it back for Joyce, I hope the term of the day for Joyce is hypsometry. That's hypsometry, hypsometry. And it's a completely unnecessary term for the vast majority. So why are we making an episode about it? I think it's an amazing bit of intuition, of geological intuition, that you can piece together these really fundamental things about a planet, our Earth, because of this curve. And so although it's a useless term, I think the term is valuable because it describes the data that we would use to get to these inferences. And it kind of aggregates all sorts of ideas about the Earth, really basic ideas from like different parts of an intro level class. I mean, you talk about erosion until the weathering and erosion chapter, and there'd be one chapter on plate tectonics, and there'd be one chapter on the oceans and stuff. But linking them all together, the hypsometric curve, the value of it is that it links them all together in this really fundamental way, I think. So that's why we did an episode on it, which might have been a tedious episode.
No, I don't think so at all. This is fun, actually. For me, anyway. You and I had fun talking about this.
Yeah. Joyce is asleep, but that's good.
Yeah,
that's normal.
She always is. I think maybe it could have been called the elevation curve or something like that. Just much simpler.
A topographic curve. I mean, something simpler. Yes. But hey, we got to get it Latin with it, and hypsometric. It's so good. Well, I don't know, Chris. What do you think?
Hey,
is that a wrap?
It is, but I have not gotten my merch yet. I ordered merch, and I haven't gotten my hat and shirt yet.
I'm sure it's on the way. So. The white glove delivery service is coming. Maybe they're knocking.
I was
your door
hoping
behind you right now.
To be able to surprise you with it today, but no go.
Oh, you got to be patient, man. It's coming.
All right, I'm not a patient person. I'll tell you that.
I know.
It's
you're
not one of my
person.
virtues.
We'll have to record with our Planet Geo hats on next time.
Yes. Yeah, can't wait.
Planet Geo hat, Planet Geo shirt. On that note, there's a couple ways to support us. You can go to our website, planetgeocast.com. We have merch now. There's a hat, a shirt. We're going to be adding some stuff to it as well, a couple different varieties of hat with the Planet Geo logo. So that's one way to support us. Another way is download our mobile app. First link in your show notes. We have a ton of visual podcast series. The main one is this course that Chris and I teach. I teach the college level, and Chris teaches basically it's college level to high schoolers. We have most of that entire course in visual podcast series there for free. You can also buy audiobooks, and some of them are podcast plus images, and some of them are standalone audiobooks on the geology of the amazing national parks that our country has to offer. You can send us an email, planetgeocast@gmail.com. You can also follow us on all the social medias @planetgeocast.
Cheers.
Peace.